It's fantastic to see you all here. About 100 years ago, perhaps that's an exaggeration, but a long time ago, I remember sitting in a room a bit like this and hearing a well-meaning but really rather stupid local councillor trying to inspire us, and all he did was scarred us for life. My cadre from that year still talk about the things that he said. I won't tell you what they were, but if you want to know, you can ask me afterwards. So I'm not going to talk about inspiration as such, but I think what we in the world of astronomy tend to do, I think, is inspiring almost without trying. So I've been asked to give you a snapshot of my life, which I'm going to do, and it's called Dark Secrets, but that's less to do with the dark secrets in my life, although you can ask me about those as well if you like, than some of the subjects that we deal with in the world of astronomy. And things that occupy a lot of my time are, as it says up there, dark matter and dark skies, but not necessarily in that order. And that's me, and that's the organisation that still pays my salary after all these years, which is wonderful. Let me take you to a place that's very close to my heart. And this is a mountaintop in northwestern New South Wales. It is in a mountain range called the Bungle range. And Bungle is a Gamilarey word. It's a beautiful name for a beautiful place. It means crooked mountains, Bungle. And in the middle of those mountains is a summit, which you can see there, that is covered in trees, but also has lots of futuristic white buildings on top, which are indeed telescope domes. And in fact, the biggest one of those is the organisation, or the telescope operated by the organisation that I work for. It's called the Anglo-Australian Telescope. In fact, the site is run by a competing university to yours, called the Australian National University, but we at the AAO, the Australian Astronomical Observatory, are completely independent. When you go there and look at the sky at night, it's rather dramatic. And it contrasts very strongly with the sky that you would see if you went out later tonight here in Sydney, assuming that it actually stopped raining. I was on the steps of the Opera House about 2 months ago and kind of sketched what I saw in terms of the stars, and that was it. The Southern Cross at the top and the two pointers. And at the same time, a colleague of mine, David Malin, was taking a picture of the same bit of sky from Siding Spring. And it looked like that. That's exactly the same bit of sky, but in a site where the sky is unpolluted by city lights. And in fact, that part of the sky is rather significant because, once again, it has strong Aboriginal symbolism. Maybe you can see the head of the emu there and its body straddling the Milky Way. Sadly, the picture is spoiled by the lights of Sydney, 350 kilometres away. That is the glow of this city. And part of my job, and really a lot about what I'm doing these days, is talking to the city fathers, city councils, to coal mines, because there are coal mines all over the state, which can be quite bright, and organisations like that, trying to explain that sending light up into the air is a bad idea because it wastes energy. And of course, wasted energy has a significant greenhouse footprint. But I haven't always been a campaigner for dark skies. That's something that's only happened within the last few decades or so. My real, I suppose, origins really take that love of the night sky and what is in it, because that really switched me on when I was a kid, and combine that with a sort of technological bent that I think is part and parcel of the fact that I was a product of my time. When I was growing up at school, we had things called world wars, and there had been one relatively recently, and everybody thought there was going to be another one. So science and technology was very strongly built into the curriculum. When I left school, I was already hooked on astronomy, and after I got my shiny new degree from St Andrews, I went and became an optical physicist, working for a company that built large telescopes. And this, in fact, is a telescope mirror. It's still in operation in Italy. It's a piece of glass, 1.8 meters in diameter and quite thick, as you can see. It's got slime running down the side because it had just come off a polishing machine. And that young laboratory physicist that you can see in the background is actually me. I don't know quite what happened to the hair, but it went somewhere. This picture actually was taken as a publicity image for the company I worked for. But my boss, who was one of the most eminent optical scientists in the country, although I was too stupid to realize that, he said, we can't possibly release that picture because it makes Fred look like an out-of-work musician, which was a very prescient remark, because not long after that I left the company to become a research student, actually once again in Scotland, to study astronomy rather than astronomical technology. And to support myself, indeed, I became an out-of-work musician. That was me in the 1970s, looking actually probably better than I was playing at the time. Fast forwarding by about 30 years, as I've explained, the place that really has imprinted itself on my soul, I think, as well as my mind, is Siding Spring Mountain. This mountain in the midst of the Bungle Range. And that dome there, the dome of the Anglo-Australian Telescope, the largest visible light telescope in Australia, has been my home for quite some time. My office is now in Sydney, but I have still got an office in that building. I often tell people I've been working in it for so many years, I've started to look like it. And maybe one day I'll have a little walkway tattooed around here, just like we've got on the telescope itself. Actually, once cracked that joke to an audience, I think it was in Adelaide, and a guy stood up and said, "I'm a tattooist, I'll do it now for you if you like." I said, no, it's just a joke. So inside that dome is a very large machine, a piece of technology which has been built for one purpose, which is to explore our place in the universe. And it's done that remarkably well for 40 years. I can't really, in the time I have, explain the technological details, except to tell you that it is, as I said, Australia's biggest visible light or optical telescope. Down in the bottom here is a mirror, a bit like the one you saw a minute ago, but twice as big. It's 3.9 meters in diameter. Sits in the bottom of the telescope and gathers light from the stars and galaxies and planets that we observe. And then it focuses that up to the top end of this tube, where there is usually a very high-tech piece of kit, which is what is used to make the measurements and analyze the information that is coming to us. Sadly, there is nowhere to look through. It's a bit of a shame, because I was drawn to astronomy as a kid because I like looking through telescopes, and we don't have anywhere to look. However, it's pretty impressive to use it. We use it in a number of ways, but the one which I guess is closest to my heart, because in some ways I helped to set this technique going back in the 1980s, is something which has a very esoteric name. We call it multifiber spectroscopy. And what it means is this. If you point a telescope at the sky, what it does is, just like a camera, it forms an image. It makes an image of the sky. And if you've got an electronic sensor, or in the olden days a photographic plate, then you will record that image, and it'll look a bit like that. But with multifiber spectroscopy, we don't do that. What we do is we use fiber optics, which you all know about. They transmit light from one place to another, and we align a fiber with each of the objects that we're interested in the field of view of the telescope, and collect the light from it. We suck the light down the fiber, and at the other end, we plug it into an instrument, which we call a spectrograph. A spectrograph is just a very fancy machine for turning light into rainbows. It basically splits the light into the spectrum of colors that make up the light of stars and galaxies. And lo and behold, when you do that, there is a barcode of information for each object, whether it's a star, a galaxy, a planet, doesn't matter what it is, it will have this barcode of information. Many of you will know about absorption lines and emission lines. That's what we're looking for. And it is that that allows us to then analyze these data, and it says the answer to life, the universe, and everything, and it's not actually that much of an exaggeration, because the trick with this technique is, I've shown 5 optical fibers there, but we can use hundreds of fibers. And what that means is, as you point your telescope to the sky, you can analyze in the most intimate detail something like 400, 500, perhaps 1,000 objects simultaneously. So when I started in this game nearly 100 years ago, you had no option but to measure the spectrum of one object at a time. Now we can do it hundreds at a time, and that has opened up a whole new area of astronomy. There is a trick to this, though, and that is that when you position the fibers, you have to do it with an accuracy of 1/100th of a millimeter. So you can't just plonk them down anywhere. You have to align them very accurately. In the very early days, the way we did that was to get a brass plate and drill holes in it which matched the positions of the stars or galaxies or whatever you were looking at, and then you could plug the fibers into those holes. We had a technical term for it. We called it stuffing the fibers. So we stuffed the fibers in the holes, and then at the other end, as I said, lined them up on the slit of a spectrograph. If you look closely, you might see the name Watson, which might be familiar to you, and that was in 1983. This was when this technique was really in its infancy. But in the 90s and early 2000s, we developed an instrument with a really rather boring name of 2DF. I built some instruments which had far better names than that, Flair and Panache and Finesse. But 2DF stands for 2-degree field. It's the amount of sky that this telescope can see, which is about 4 times the diameter of the moon. It's a very, very large chunk of sky. And 2DF is the instrument that we now use to look at the sky with this fiber optic trick. We have a very clever robot which sits actually at the top of the telescope tube. The telescope's horizontal in this image. Down there is the 3.9 meter mirror I was telling you about. And what the robot does is it picks up these fibers which have a little magnet attached to them and puts them down in the correct position on a steel plate. They have a little prism on the end to reflect the light. So that's how you get this 1/100th of a millimeter positioning. The problem with this is it has to do them one at a time. So you have to have 2 of these plates. So one is actually making the measurements while the other one is being set up. We have another telescope at Siding Spring, one which is even closer to my heart. It's called the United Kingdom Schmidt Telescope. It used to be run by the Royal Observatory Edinburgh, and it's what brought me to Australia for the first time to live in 1982. That's a beautiful portrait of the dome as we got ready for a night's work, except the photographer didn't like my car, so he took it out, as you do if you're good at Photoshop. But the telescope itself was built for photography, but we now do this fiber optic trick with it, and we are on the point of building a completely new technology, which will, I think in a great way, it will combine the inspiration of the science that we can do, which I'll explain in a minute, with the technology, which really is leading edge technology, because we now dispense with the robot that picks up each individual fiber, and we build the robots into the fibers themselves. These are tiny little autonomous robots which will move to wherever you want them to. They're about 8 millimeters in diameter, those things. This is new technology which we're currently developing at our laboratory in North Ryde, not very far from here. So really quite remarkable stuff. Now, why do we want to do all this magic technology? I thought I might very briefly give you a case study for the kind of science that we do. And it centers around something we call dark matter. Dark matter is something that astronomers are obsessed with, and I hope you'll see why in a moment. But it's quite a long story. It's surprisingly long. Most physicists think we've only been talking about dark matter for a decade or so, but it actually goes back to this scientist here, who made some observations in the 1930s that were rather remarkable. His name was Fritz Zwicky, and as you can see, he lived for most of the first 3/4 of the 20th century. You can probably get an impression from looking at him that he was quite a character, and indeed he was. He was one of these astronomers who did not suffer fools gladly, and he's on the record as having described some of his colleagues as spherical bastards. And when he was asked why they were spherical and not just ordinary bastards, he said, because they're bastards whichever way you look at them. So they must be spheres, because that's the only a sphere is the same whichever way you look at them. So Fritz Zwicky was, as I said, a character and a half. But in the 1930s, he was observing galaxies. Now, I haven't actually told you what a galaxy is, but I will in a minute. Let me say for now they are aggregations of typically 100 billion stars. We live in one, we call it the Milky Way galaxy. You saw the edge of it at the beginning of my talk. But these things actually they're like sheep, and they're gregarious, so they come in clusters. And Zwicky in 1933 was observing a cluster of galaxies in the northern hemisphere constellation of Coma Berenices. Berenice's hair, a lovely name. We can't see Coma very clearly from down here in the south, but he could with the telescopes he was using. That's a picture of the Coma cluster. Every blob you can see there is actually a galaxy with 100 billion stars in it, or thereabouts. There's one star which belongs to our own galaxy, so that's in the near foreground. So what he realized when he looked at these galaxies with his spectrograph was that they were moving too fast for the gravity of the cluster to hold on to them. And he realized that it would need far more stuff than he could see for gravity to hold this cluster together. He was very surprised at that. There you are, I told you he was surprised. He swore in German, of course. But he made really a profound deduction, and that was that there was something in this cluster which was invisible or dark, something that he couldn't see. And that is what we now call dark matter. It went through, I guess, a resurgence of interest in the 1970s, because in Zwicky's time, nobody could understand what it was all about, so they ignored it. By the 1970s, though, with astronomers like Ken Freeman, who also is not not a UNSW astronomer, but I'm sure he would be if he could be. He's at the ANU. Ken Freeman and a lady called Vera Rubin, who's an American scientist, they really put the idea of dark matter on the map when they realized that galaxies were actually turning too fast to stay together. Here's a beautiful galaxy, a beautiful object photographed by the Hubble Space Telescope. Astronomers tend to take beautiful things and give them ugly names. This is called NGC 1300. It's as good a name as we can give it. Similar to our galaxy, as I said, except ours has a slightly smaller bar across the middle. But we know that these galaxies are going around too fast to stay together. They should fly apart, if it were not for this mystical stuff, almost, dark matter. And so modern measurements of galaxies actually reveal, first of all, that dark matter likes to be where normal matter is, so it's in this room, probably, and also that it outweighs normal matter by about 5 to 1. So for every kilogram of normal matter in the universe, there are 5 kilograms of dark matter. And we don't know what it is. The two principal theories in the 1980s were machos, which were massive compact halo objects, perhaps black holes that you couldn't see, or orphan planets or dead stars. And the alternative, which is the one we now believe to be the case, is WIMPs, machos and WIMPs, of course, weakly interacting massive particles, some species of subatomic particle whose nature we don't know. Now, the story of this has really switched now to machines like the Large Hadron Collider, where people can actually probe these very small scales. But for astronomers, I think there is still a role mapping the distortions of space, which we can do to inspect where dark matter is. That's had a spin-off, which is really where I want to end this little presentation, because this is something very important to me. And that is that as well as mapping and providing hard scientific data, we also produce some things which are spectacularly beautiful. And what we have here is actually a representation of a survey of galaxies in the local universe. That's out to about 500 million light years, made with the Schmidt telescope, the one I showed you earlier. And it's a simulation because you can't actually deal with this sort of data set in reality. But what we've done here is put together a map which looks boring until you start flying through it. Because the only way to visualize a three-dimensional collection of galaxies is really to fly through them. And this takes our survey data. It's footage that was produced by another university, not in Sydney this time, actually Swinburne, where they do this kind of thing. And what we've done is for every galaxy that we have measured, we've put an image of a similar galaxy. So they're not the real ones, but they're images of similar galaxies. But nevertheless, the positions are the correct positions. And what it tells you is that the universe is not uniform. There are voids in it. There are sheets of galaxies, some of which you can see kind of going past. There are filaments, and these are all a result of the action of dark matter. I worked out when I first saw this that you're actually traveling at an equivalent speed of 100 trillion times the speed of light in this simulation, which of course is impossible by relativity, but nevertheless it gives a great idea of what the universe looks like on very large scales. And I think in many ways encapsulates the excitement of science as a whole, because we see beautiful things. We have the most extraordinary discoveries awaiting us, the nature of dark matter. In 20 years' time, we might be using dark matter in a mobile phone or something. Who knows? We just do not know where it will lead. And that's the great joy of science, the unknown. It's all about curiosity. So let me wind up there, because science is something that I can't help but get excited about. And I hope that those of you who will pursue science in this audience will feel the same kind of excitement. Thanks very much, everybody. Thank you. Thank you, everybody.